In this presentation, I will focus on data science for shales. As you probably know, shales become recently a very attractive way of producing oil through very unconventional means, in particular through hydraulic fracturing. There will be a series of presentations, and I will focus on specific aspects, but you can also see that perhaps the presentation should be seen as a totality, in its totality, as an approach to a data scientific approach to reservoir forecasting for shales. In this presentation, I will mention functional principal component analysis and Dice Kriging. The presentation is, in fact, this presentation is in fact a reflection of a presentation that was given in 2015 at the annual technical conference and exhibition of the Society of Petroleum Engineers. And I want to acknowledge here the work done by my former PhD student, Ognan Grucic, and also Carla da Silva from Anadarko Petroleum, who provided a lot of the data sets that we are working in this project. Shales are ubiquitous in the United States and have become quite a new important assets in terms of reserves and production. So there are various of what are called shale plays. And some of the known names are Marcellus Shale, the Eagle Ford Shale, the Barnett Shale, and other areas in the area of Colorado and the Dakotas. Not just in the United States, but also worldwide, we see that many of these deposits or reservoirs have been discovered and are currently being investigated. So this offers a whole new opportunity to look at how we can use data scientific methods on very large scale, simply because in these types of reservoirs, as we will see, we get a lot of information since the drilling occurs at much higher speed than, say, on conventional systems. Shales are in fact a rather poorly understood rock if it comes down to its reservoir capacity. That's simply because in conventional systems we don't often study shale in great detail. We focus more on those rocks that contain the fluids, which is the high porosity, high permeability systems such as sandstones. Shales are highly rich in organic content. They have quite significant porosity, but of course have very low permeability in the millidar range. So in order to access, therefore, the hydrocarbons that are trapped in the shale, we need to perform hydraulic fracturing, which is a method by which chemicals or fluids are pumped at high pressure in the subsurface at various stages, and fractures are created such that that oil and gas flows out of these fracture system into the producing well. So here we'll work on a real shale forecasting problem, a data set provided to us by Anadarko. So in this data set, we actually have quite a limited amount of wells, which for shale development is still very limited, simply because the system was still under development. Later in the other presentations, I will mention case studies with several thousands of wells. The nice thing about this data set is that we have pretty much all the observations in great detail. That means, first of all, that we have the data of production, oil production, water production, gas production, as well as other types of information that is useful in the data analysis. And so this at the bottom here, let me turn on my pointer. At the bottom here, we see the various production curves at the various well locations in this particular field. So you notice a couple of things. First of all, you notice that the data is very noisy. A lot has to do with well downtime and other kind of manual operations that are happening. And also that the production starts for these wells, of course, in different time periods. So not all the wells are being produced at the same time. Often we walk around over display and we learn from the kind of experience we have in hydraulic fracturing and therefore adjusting our way of producing the reservoirs. So this suggests that learning and statistical analysis, machine learning, data science can play an important role, simply because very few of these operators actually build significant reservoir models. Often the drilling is done simply rather very fast and adjusting things as we go along. So the information that we get, as we said, is the production that we get, but also, of course, the location of the well, where it is located. We have measure in those well petrophysical properties, or often these are derived from seismic, or not seismic, geophysical attributes, other types of surveys. So these are often averages, average porosity, water saturation, etc. And then we have a set of parameters, fracking parameters. So you could see this as geological parameters. We have no control over those. Those just exist. And these are the hydraulic fracturing parameters. So this is sort of the parameters that are man-made and created. So the production evidently will be a function of space. It will be a function of the petrophysics, geology, and it will be a function of the completion variables. Throughout the presentations I will be giving on this data science for shale, I'll mention several objectives and questions that are relevant and be starting to address those. So of course, important to engineering in general is to understand relationships between the parameters that are there and the production that we have. If we get that understanding of that relationship, we can generate a predictive model. So here we have to understand that there are two sets of parameters. First set of parameters are geological parameters, and the set of parameters are the completion parameters. So given then, of course, what we have observed at existing wells, can we then forecast production at some new location? So there's basically two elements to that. First of all is that this new location will be somewhere else geographically. So this is a spatial problem essentially. And so this begs perhaps methods of geostatistics where we start to interpolate this kind of information in space. And of course, the information we are trying to interpolate, or the variable we're trying to interpolate, is a gas or oil decline rate. So we have to deal with functional information. And then secondly, of course, once we start have selected location, can we identify what are optimal sites for that location, given what we have learned in other wells? So, as I mentioned before, the production rates are a function of the geology. The completion parameters are also a function of the start date. So, in what comes next, we'll often do the following. That is, we'll remove the start date by moving all the wells into a different location. There are some assumptions, of course, being made that there's somewhat of an independence, not complete independence, but somewhat of an independence between these various wells. Now, some of you who have some experience with this will question that, of course, because when we have several lateral wells, then of course could potentially be cross-flow between the wells. But here we're talking about several, say, leases where a production is aggregated. Another thing that could address this question is to make the start date a part of the variables, the parameters on which we have control, so that would be an additional covariate or variable of parameter in the estimation problem. So instead of the traditional geomodeling workflow, where we build models of geology and then we do flow simulation, we'll here do a different approach with statistics and machine learning. I just want to mention that people have looked at this in a different way as well. Traditional way of modeling decline in these in reservoirs in general is to decline curve analysis. This basically means, let me put up my pointer. It basically means that we're going to assume a certain type of equation that we believe is a reflection of the bulk behavior of the system, and then fit the certain parameters, such as what is the initial rate, and what are decline parameters. Now, these work fine for more conventional systems, but don't apply necessarily to these unconventional systems where we do hydraulic fracturation. And several people have investigated this and found that indeed these decline curve analysis can actually lead to quite meaningless results, such as infinite decline, etc. So we will not be using this kind of parametric approach. Instead, our methods will be non-parametric. So our method is indeed non-parametric. And the method that we'll be using is generally called functional data analysis. And this is the work that has been developed in the book by Ramsey and Silverman, and I highly recommend looking up that book. These methods of functional data analysis are quite powerful for the kind of problems that we are looking at. And the kind of problems that we are looking at, to which functional data analysis lends itself very well, are problems where we have some kind of a physical behavior. So there's something that determines systematically what is going on. We have a decline, for example. This is not a random time series, or a time series with some kind of a correlation coefficient, or sorry, range in it. But that's a very systematic behavior, as we see here. So the way functional data analysis works is that the fundamental first part we do is to write basically our behavior, our data, as a linear combination of basis functions. And these basis functions are fixed functions. Now we can choose many kind of functions. And for this kind of applications, we're often stuck to spline functions, and that's worked for most of the case studies, or actually for all of the case studies that we have been looking at that use this, that have this kind of production behavior. So what that gives us is that if we do that for all of the data that are there, and remember we have 172 of these observations, then we can all fit this this data with this basically this basis expansion. In doing so, we have to count a little bit for issues related to noise. So obviously we don't want to fit noise. So we want to get a smooth curve. So there's some. First of all, we have a penalty function that has to do with the curvature of that fit. So here we have a smoothing parameter. And also the number of basis function is something that needs to be determined. And so functional data analysis are methods that allow you to do that by means of cross-validation and other types of methods. So the result of this exercise is basically is that we turn this functional observation, as we see here, something as function of t, into multivariate observations or multivariate variables. And this is a powerful idea because now we can apply any kind of multivariate statistical method on the coefficient c. Remember that these basis functions are fixed, so these are considered to be known or determined. So the only thing we have left as an uncertainty or something to be estimated are the coefficients c. So what we then have as a result after all that fitting is that we have turned all of our data, remember this was the oil rate data that was very noisy, and we've turned all this oil rate data into these kind of more smooth behaving curves. So recall that the end of the day, what we get are the estimates of the coefficient c. And so functional PCA is actually nothing more than doing principal component analysis on these coefficients. And just like that principal component analysis, what we then get are essentially eigenvalues and eigenvectors. The eigenvectors are now functions though. So this is a little bit different from traditional PCA. So here we see the various eigenvectors. So for example, the first eigenvector is a function, and that seems to represent something that declines over time. So that is this black line. The second eigenvector is something that seems to reach a peak at some particular point. And the third eigenvector is even more complicated, has a peak and a trough and a peak. So these are the three eigenvectors, the first three eigenvectors. We also get, just like in principal component analysis, we get the contribution of variance of each of these particular eigenvectors or eigenvalues. And so we notice that the decline can be explains, this basic decline explains 90% of variance. The second one, the red one, has an additional, let's see, it's about 7%. And so we go up very quickly. So we notice that very quickly we can represent all this information, say, with three variables instead of a number of basis coefficients that are being fit. So that's good news. It basically means that that we can reduce all this information into basically three scores, and the scores are given to this eigenvectors. So these eigenvectors are also called harmonics, and that has somewhat to do with physics, where we can explain behavior of something that's moving by a few functions. So then it's also common to do and plot what these functional principal components describe. For example, as you remember, the first principal component seems to be this variation, and here I have some deviation around that variation. And the second principal component seems to be this kink here. And so what we notice is that the variation around this principal or the mean of this function here seems to be that there's a change here at this particular nick point. So it seems like after 100 days, the traditional decline model seems to be changing. And so this is often explained that by the fact that after some time, the kind of behavior we get is that gas is determined by the completion versus gas being, the production being determined by completion, changes in mode to production determined by geological factors or by reserves. And so this is actually has some kind of a physical meaning. But again, we notice that that 98% or something in that nature of these functions of these principal component can explain this entire variation, and that's quite a powerful result. Just like with principal component analysis, we can then calculate principal component scores. And so just like with principal component analysis, and this is just expressions of these scores, and these are the harmonic functions. So instead of a sum, we get an integral. And here we get, just like with principal component analysis, we get the principal component scores on these various functional principal components. This also suggests now doing sensitivity analysis. What do I mean by that? Let's put my pointer. So we have our principal component score. So remember that each score here represents one single decline. We also know for that decline data set or that particular decline sample, we have parameters, to be geological parameters or completion parameters. So what I'll now do is essentially color code each of these dots with that parameters, and this is the result we get. So here we notice, for example, that this is a principal component score of one particular parameter. I don't exactly remember which one it is, but it's clearly that this parameter has a sensitivity. The production is sensitive to this parameter, because we notice that in this part of the score plot, we mostly have red or yellow dots. In this part of the score plot, we mostly have blue dots. So this is also a neat way of doing sensitivity analysis. To formalize that a little bit, we'll do distance-based generalized sensitivity analysis. And here I refer to this presentation that's narrated on sensitivity analysis and global sensitivity analysis in general. So basically what is being done is we make two groups, a blue group and a red group, and that is based on the principal components. This is our clustering that's involved, and I'm not going to go into detail where the clustering is involved, but imagine that these are two groups that are being created. Then for each group, I can look at the color and I can make a histogram of that color. Here we see the number of stages is the parameter that is being investigated. So the number of stages essentially is that the well is divided into sections, and each section is being fractured separately. So of course, the more stages you use, the more production you will get, but also the more stages you use, the more expense you have, since each stage costs an amount of money. So we notice in the red group is that we get a different number of stages than in the blue group, and that has an effect. The black here is just the combination of the two. So in distance-based generalized sensitivity analysis, we calculate sensitivity by looking at the difference between these various CDFs. So now we can start doing that for all of the parameters. For example, let me put my pointer. This was the number of stages. Here we have the amount of fluid that's pumped in. Of course, that has an effect clearly. And here we have some geological parameters, which is the API gravity. And then there's a number of parameters that are less sensitive. And a bit surprising is that most of the geological parameters are not sensitive. And part of the reason for that is not because geology is not important, is that because these parameters are typically, the way they are given or calculated, are typically averages. And so averages seem to not have, averages of geology does not seem to have a big influence on the production. So in order to see the influence of production, we have to probably parameterize the geological parameters in different ways, or get that information in different ways. Then we can also sort of summarize that into a Pareto chart. And so here we see what's important are typical the completion parameters, also where the well is located. So that's actually a geological parameter because we have geological variation over the basin. So this parameter is reflecting of geology. That's actually important, but it's just sort of a general parameter, not a specific one. And then we have all these average geological parameters that have very little sensitivity. Okay, so we have talked about functional principal component analysis, a method, or first functional data analysis, whereby we can represent noisy data by these smoother curves. A method of functional principal component analysis, where we can do dimension reduction and represent all these curves with a score plot and scores given to functional principal components. Then I also suggest that if I want to predict something new, then the only thing I probably would need is a few principal components, that every production profile can be reconstructed as such. For example, here we see that the first would be simply the mean. So I can write my production decline as a mean. And for example, this would be that mean function, which is simply the mean of production of all these functions here. Let me put in my pointer. So this is the mean function. That's that's basically the mean of all these curves. And so if I take down one particular decline, and I see that the only thing I get is sort of the same trend, but I get a lot of error. In order to improve on that, I can add the second harmonic, second vector basically, and add a new score. And you can see that I get a better fit, and I can go on and on like that. And we notice that after 2 here, that we get already a reasonable good fit. And that's what we saw previously in the previous slides. So this is interesting now, because this suggests now that in order for me to estimate something new, an unseen production decline, the only thing I need to estimate are these two scalars. And so that reduces the problem of estimating a function to estimating two scalars. And for that, we can use simple regression methods. So this is then shown here. We assume that our functions, sorry, put my pointer again, that our functions are known, constant, probably not known, but they're estimated. In order to forecast a new well, I need to estimate these coefficients. So by definition, of course, these are independent because of their covariance is zero, at least empirically. And so that means that I can try to estimate these two independently as function of the various fracking factor parameters and geological parameters. So there's not quite a number of parameters here. You saw in the previous slides, maybe there are 20, 30 parameters. And so we can therefore develop a simple regression model. So the easiest way to do this is ordinary least squares regression. So what we do here is we have, let's see, we estimate the first principal component. We do the ordinary least square regression, and we observe the residual behavior in order to see whether or not there's some kind of nonlinearity that we're not capturing. And it seems that these residual are quite well behaved, and so a linear regression technique seems to work quite well. So we use ordinary least squares to predict the scores and therefore forecast these production curves. So this is then the predictions, and this is the variance that we get on the prediction. So in order to start comparing methods with each other, we're going to introduce this error, the mean absolute percentage error, which is basically, or called MAPE, which is the error calculated over the time. So we have 400 time steps. This is the curve, this is the average curve, and this is a relative difference. So here you see a couple of examples of that MAPE estimate. We see we have withheld some test data essentially. I forgot to mention that in the previous slide, but we have withheld some test data so we can evaluate how well our method is predicting. And so here is the actual smoothed, so it's not actual data, but it's the smoothed data. This is our estimate, and this is our 95% confidence interval. So here, for example, for a particular well pad, we have a MAPE of 12%. WellPad 23 is even better, 4.3%, 9.8%, 24%. So now we see that the confidence interval no longer covers the truth, although that is, of course, expected in some cases for a 95% confidence interval, etc. So an average MAPE we get at the end is about 24%. Okay, so that's a linear regression, or ordinary least squares is basically you're fitting a plane through data. Another method of doing regression is kriging. So recall that in kriging, in spatial kriging, what we're doing is we have observations in space, and we'd like to predict some unknown observation. So a linear regression method will just fit a plane to this data. A kriging method will actually try to interpolate this data with a local linear model. So we write essentially that the unknown is a linear combination of some observations. So now we're not in space. Here we are in the space of the parameters. So this is a very high dimensional space. So if I have n parameters, then essentially I have an n-dimensional space where each of them I have an observation of or a realization of a parameter. Now this is xi here. So the xi are the set of parameters that I have observed at a particular location. So we can extend this idea of kriging, spatial kriging, to kriging within the parameter space. And this has been developed by David Gainsbourget of the University of Bern, which is called Dice Kriging. And it's also used for analyzing computer experiments, for building surrogate models for computer experiments. So these are the same techniques. So that also means that the equations are exactly the same as the kriging equations. I'm not going to go over this in detail, but that the mean kriging is a function of the covariance matrix and the relationship or the covariance between the unknown and the data points, and that the kriging variance is a function as well of this matrix and this vector, and this is basically the variance of the data. The only problem we have here is that we are much higher dimensions, say, than 2 or 3 dimensions, so making variograms is much more difficult. And to do that, we'll have to rely on parameterized model. In particular, we use the Matern covariance kernel and some fitting procedures for these n-dimensional models that we're not going to go into here. And those are because those are basically part of this Dice Kriging package. So then we can compare ordinary least squares versus the kriging. And so again, with kriging, we get a confidence band. And so we can look at a few cases. So here, we see kriging seems to do a bit better. Again, a bit better. Here they seem to do relatively well, both of them. Same case here. You also notice, for example, that the confidence bands of the ordinary least squares are much smaller than the confidence bands given by kriging, and that's something we'll comment on in the next slide. Again, here the confidence bands seem to be very similar. Again, we get a wider confidence band, seem to get a better estimate, etc. Okay, so we can summarize all these results. So here we see again that we have retained some data for testing and some data for training. So the blue dots are the testing, red dots are the training. Remember, these are the location of the wells. And so again, we look at this MAPE and the mean MAPE. And we notice that if you compare ordinary least square with kriging, that the average error is pretty much similar. There's not a whole lot of difference. But that if you look at the confidence bands, that with kriging we get, we predict basically 86% of the time that we are within the 95% confidence band. So that means in terms of the prediction of the confidence band, we get much more accurate results or realistic results than we do with ordinary least squares. And this is actually known for when you compare kriging and ordinary least square in general. So the kriging technique here is superior in that sense. Okay, this brings us to the end of the presentation. So just a final summary. I think we've seen that we can take noisy data that's functional, meaning having some kind of physical process behind it, use functional data analysis and functional principal component analysis to set up a low dimensional system. So that allows for easy data mining, sensitivity analysis, and also allows for forecasting with multivariate or Dice Kriging and ordinary least squares. So a lot of these codes are available. For example, the Dice Kriging package by David Gainsbourger. I have here some references related to that. I don't see David's code. Yes, I do see here at the top. So that's available. The book by Ramsey and Silverman is a really good reference for that as well. So we have also our own codes and references. These are generally other topics as well, and I will mention these references in the following presentation on this topic. There's also codes and packages that have been developed by my PhD student, and so those are also available for your use. I hope you enjoyed the presentation.